All right, guys, welcome to section 3.6. We are going to be looking at more derivatives, of course, but we're going to be looking at derivatives of logarithms. Okay, so we're just going to hop to it. The derivative of a logarithm, let's use our notation d dx, of log base b of x is equal to 1 over x times the natural log of the base b. Okay, so this is one to memorize, so I'm going to put it in a little box. And we're also going to prove it. So let's look at the proof of this derivative. So here is our proof. Okay, so let's define our function to be log base b of x. All right, and now we want to find y prime if we want to prove this box right here. Okay, so this is our logarithm, and we're going to find the right hand side. We're going to find that derivative. So remember, a logarithm, it's the inverse function of an exponential function. So we can rewrite this in exponential form. It's base b. A logarithm is an exponent, so y is equal to the logarithm, so y is the exponent, and now it equals to the argument of the logarithm. Okay, so I haven't done anything. I've just rewritten a logarithm into its exponential form. And now we are going to do our implicit differentiation. So we know for implicit differentiation, we're going to come in and we're going to take the derivative of both sides with respect to x. All right, and it's with respect to x. So if we have any variable like y, we have to assume that y is a function of x. Okay, so let's see what that's going to look like. So we know how to take the derivative of an exponential. It's going to be b to the y times the natural log of the base. Okay, so that's the derivative of the outside function, the exponential function. And now we're going to take the derivative of the inside function. That's our chain rule. All right, so again, using the chain rule, we're going to take the derivative of y. But remember, we're taking the derivative with respect to x. So we're going to write that as dy dx, or y prime, right? Okay, then on the other side, we're taking the derivative of x with respect to x. So that's just going to be 1. Okay, so what are we doing? Well, we want to get an equation for y prime. So we're going to keep that dy dx on the left, and we're going to move everything else to the right. So this is multiplying, so we are going to divide both sides by the coefficient of y prime, or the coefficient of dy dx. All right, so we're solving for that highlighted part. All right, so where are we at? We're at dy dx is equal to 1 over b to the y natural log of b. And right now we have an equation for y prime, which is what we want. Remember, that's our motive up here. But we started off at the function of x, right? Y was only in terms of x. And right now our derivative has a y in it, which doesn't make sense. So we have to get rid of that y. And luckily, we have an equation for y. We know that y is equal to log base b of x. So we're going to make that substitution. Okay, so dy dx is equal to 1 over b to the y, but y is just log base b of x times the natural log of b. All right, and we're almost done. We have a property. It's kind of it is the composition of inverse functions. The composition of inverse functions is the identity function. All right, so again, this expression log base b of x is the exponent of b that gives us x. It's an exponent that gives us x. So b to that exponent is x, okay? So we're going to replace that thing with x. And then we have natural log of b. Okay, and then that's exactly what we were trying to prove. We were trying to show that the derivative with respect to x of log base b of x is equal to that expression. And we just proved it. So remember, when we're done with proofs, we can do a square and we can color it in. Okay, so again, one to memorize. And then we have a special case of this derivative. What happens if our base is e? What kind of logarithm do we have then? Whoa. Okay, we'll switch over to rainbow. We have the natural logarithm when the base is b, right? So let's look at our equation in that case. So we would have 1 over x, natural log of the base, but the natural log, or the base is e. So what's the natural log of e? E to what power is e? It's 1. So we're left with x times 1, which is just x. So the other one we should memorize is that the derivative of the natural logarithm is simply 1 over x. All right, so that's a nice consequence. Okay, so let's hop right in and let's try some problems. The instructions would be to find the derivative. And we'll just do some relatively straightforward ones that combine some of our previous derivative laws. And we'll start with this, the natural log of the cosine of x. And then we can also start with the logarithm of the square root of x. Okay, and you guys can definitely try this on your own, so go ahead and push pause and try it on your own. A little reminder, what happens when, well, natural log, we know the base is e, right? But if there's no base on a logarithm, what does that mean? An invisible base on a logarithm is base 10. All right, so keep that in mind when you're doing your solutions. Okay, so if you push pause, welcome back. Let's see how you guys did on these problems right here. Okay, so number 1, your solution, we have to use the chain rule, right? Because we have an inside function and an outside function. The inside function is cosine, outside function is natural log. So we can go about it a couple different ways. Remember, we can introduce, whoops, I didn't label these. We'll just call them y. We can introduce another variable u, and we can look at the natural log of u, where u is a function of x and it's equal to cosine, right? And then we just plug in the u. So that way we can clearly see the inside function and outside function. And then we know from our chain rule that this is going to be equal to the derivative of the natural log with respect to u, and then times du dx. So again, derivative of the outside function times the derivative of the inside function. Okay, so the natural log of u, we just learned that derivative. And natural log is the fun one because we don't have to worry about the natural log of b, right? It's just 1 over u. And du dx, what's the derivative of cosine negative sine? Okay. And then let's make a final substitution. What are we calling u? U is just cosine of x. All right, so we're looking at 1 over cosine x times negative sine of x. We can definitely clean that up a little bit. We'll move the negative to the front. And then what's sine over cosine? its tangent. So that gets you, oops, to the solution. The derivative of that function was negative tangent. So the natural log of cosine, if we took that derivative, it's negative tangent. Okay, let's see how you guys did on number 2. We're taking the logarithm of the square root of x. Okay, so log square root of x. Remember, it's nice to rewrite square roots as exponents. It's helpful to find the derivative. And again, we can just hop right into the derivative by taking the derivative of the outside function times the derivative of the inside function. Some people also like to introduce a u, so we can clearly see the outside function, and then u is the inside function. All right, and it's a matter of preference. Okay, so then y prime, we're going to take the derivative of the outside function. So the derivative of the log of u is 1 over u times the natural log of, what's the base again? Invisible base is base 10. Okay, so there you go. And then we have du dx. So I can write it right there for now because that was kind of a lot. All right, so let's start making our substitutions. U, again, is, what are we calling u? X to the 1/2, or square root of x, natural log of 10. And then what's u prime? Let's do a little side work so we don't have too many lines. U prime, we can use our power rule, so bring down the exponent and then subtract 1 for the new exponent. Okay, 1/2 minus 1 is negative 1/2. Negative exponents, we can send that downstairs. With the 2. And then x to the 1/2, again, is just root x. X to the 1/2 is root x. All right, so that's what u prime is. Kind of a long derivative. Okay, so we can clean this up. We can perform that multiplication. So multiply the tops for fractions. And then down here, let's see, we have a root x times root x, which is just going to be x. And then we have the 2. So root x times root x, that's like root x squared. And we have the natural log of 10. Okay, so there you go. All right, so finding the derivative of logarithms, it's just another tool in our toolkit to help us find derivatives of these really complicated functions. Let's see another technique that we can use with these derivatives. And let's say that we were going to find the derivative of h with respect to z, so h is a function of z, if h of z is equal to the natural log, and then we're going to introduce a complicated argument, the square root of a squared minus z squared divided by a squared plus z squared. Okay, and then let me show you this. Notice in our derivative, we're taking the derivative with respect to z, and notice that h is a function of z, all right? That means that this a right here is behaving as a constant, okay? So since h is just a function of z, that's telling us that a is a constant. All right, so sometimes that happens. So we're looking at a as a constant. Okay, so we see our natural logarithm. We definitely see this as a chain rule, right? We have an inside function, an outside function and an inside function. And even notice with the inside function, think about taking the derivative of the inside function. Again, we'd have to use the chain rule because there's an outside function and an inside function just of the argument. And then on the inside function, we would also have to use the quotient rule. So this would be very, very involved if we were to just use one chain rule right off the bat. Okay, so strategically, there is another way to approach it. And what we can do is we can use our logarithm rules. So because our argument is so complicated, we definitely could just go for it and, use the chain rule twice and then use the quotient rule. Or we can simplify this expression and use logarithm rules. So that's going to be our strategy because it's a little bit complicated. Okay, so let's see what this is going to look like. First of all, what do we do with square roots or any nth root? It's helpful to rewrite it as an exponent. All right, and then when our argument has an exponent, what can we do with that exponent? We can bring the exponent to the front. So that's one of the logarithm rules. So that's the kind of stuff I'm talking about. We can rewrite this one logarithm and we could separate it out using our logarithm rules. All right, and then for those that need a little refresher, remember that logarithm, if we have the natural log of a to the nth, we can move the n in front. Something like that. Okay, so that's what that step was telling us to do. All right, and then now we have a division of arguments. What happens if we're taking the logarithm and our argument is being divided? We can take the natural log of each, right? So we can separate them and we can subtract the denominator minus the natural log of the numerator minus the natural logarithm of the denominator. All right, so that's what we're going to do here. So let's write that out. It's another logarithm rule. And let's make sure we're going to be putting parentheses around that. So we multiply both parts of our difference by 1/2, not just the first. It has to be balanced. All right, and then just kind of reflecting on that, is there anything else we can do? No, this is as far as we can separate it out, okay? We can only separate an argument if it's a quotient, if it's a product, or if the entire argument is raised to an exponent, okay? So right now, a squared minus z squared, that's all we can do. So now we're ready. So this is still equal to h of z. We haven't changed anything. Everything we've done is legal. And now this is going to be a lot easier to take the derivative of. Because when we take the derivative now, here I'll switch colors since we're actually doing something now. Let's see, when we take the derivative, we can worry about constants in front later. And we can take the derivative of the first part of the difference right there, minus the derivative of the second part. Whoops, I lost the natural log. All right, and it's going to be a little bit more manageable, which is the motivation for this. It's a little bit easier than doing the chain rule twice and then the quotient rule. So let's see what we get, okay? So we still have to use the chain rule. So if we take the derivative of the natural log first, remember the derivative of natural log of x is 1 over x. So it's going to be 1 over the argument, 1 over u, if you will. And then we're going to do the derivative, I can write it out like this, of a squared minus z squared. And remember, a is acting as a constant. All right, and then minus, and rinse, wash, and repeat, the derivative of the natural log of u is just 1 over u, so 1 over the argument. And then the derivative of the inside function, oof. Okay, let's see what we have. So 1 over this. And what's the derivative of a squared minus z squared? Well, constant is 0, so that's going to go to 0. And then minus, let's bring down our exponent, minus 2z, 2 minus 1 is 1. So negative 2z. And we'll do it over yonder. What's the derivative of a squared plus z squared? 0. Derivative of a constant is 0 plus 2z. All right, so we're going to be multiplying that by 2z. All right, so look at this is kind of nice because when we are multiplying, when we're going to distribute the 1/2 to the first and the second term, this is the first term, this is the second term. All right, the 1/2 and the 2 is going to cancel in both places. Isn't that nice? So I'm going to do that. I love canceling. So I'm going to go ahead and cancel that. All right, so again, that would happen when we distribute the 1/2 to the first term and the second term. All right, so now what do we have? So equals then, we have negative z over a squared minus z squared, and then minus z over a squared plus z squared. Okay, and then that's fine. You guys can leave it like that. I'm okay with that, right? Because we took the derivative. Remember what I say as far as simplifying goes. I would like you to take the derivative using all the fancy rules and then simplify it by, removing the parentheses and just, doing some basic simplification, basic addition and subtraction of like terms, all that stuff. Okay, so there you go. All right, let's have you guys try an example where you have a complicated argument of a logarithm and you clean up the function using your logarithm rules, and then you find the derivative. Okay, so you're going to find the derivative if f of x is equal to the natural log of 3x minus 5 to the 7th over the cubed root of 3x squared plus 1. All right, so remember, you could just go ahead and take the derivatives as we see this, right? So you have your outside function, the natural log, and your inside function is this whole argument, okay? So you take the derivative of the outside function, derivative of the inside function. But then look at the derivative of the inside function. You would have to first do a quotient rule, then you'd have to do a chain rule, and then you would have to do another chain rule. All right, so a lot going on. So use your logarithm rules, separate out that natural logarithm into as many terms as possible, and then take the derivative. So go ahead and push pause and see how you guys do. Okay, guys, welcome back. Let's see how you guys did. Okay, so what can we do first? So the whole argument isn't being raised to a power, right? So we can't just bring the 7 out in front here because the denominator isn't being raised to the 7th power. The denominator is being raised to the 1/3 power. So the first thing we would do is we would have to separate that using your quotient rule. And if you don't mind, I'm just going to switch that cubed root to 1/3 exponent. All right, and then once you guys write that, now we can bring the exponent to the front because now the entire argument is being raised to the 7th. The entire argument is being raised to the 1/3. Okay, and now what? That's it, right? So we can only do kind of 2 steps of this. We cannot separate this because it's a difference. It's not a product or a quotient. And likewise here, we can't separate that because it's not a product or a quotient. So this is equal to f of x, and now we're ready to take the derivative, what the question was actually asking us to do. All right, so here we go. So the first part, we can take the derivative of the first part. So we can worry about the constant at the end. The derivative of the natural logarithm is 1 over the argument, 1 over 3x minus 5. Okay, and we have to use the chain rule. What's the derivative of the inside function? 3. Okay, let's see how you do on the second term. So we'll worry about the constant at the end. What's the derivative of the natural logarithm, the outside function? 1 over the argument. And now chain rule says multiply by the derivative of the inside function. This is going to be 2 down in front. 3 times 2 is 6. 2 minus 1 is 1. And what's the derivative of 1? It's 0. All right. So that's us using our derivative rules. Now, of course, we have to clean up everything. So what can we do? So our derivative, what's on top in this first term? We have a 7 times 1 times 3. So 7 times 3 is 21. All right, and then over here, let's see, we're going to keep the minus sign. We're going to have a 6 in the top, and then that is going to cancel with a 3. So what's going to be left? A 2x in the top. Over 3x squared plus 1. Okay, and then that's that. Remember, a common mistake, let's just talk about a quick common mistake, is you look at that second term and you see this x right here and you go to cancel it. That's illegal. You're not allowed to cancel terms. The only way you could cancel this x and this x right here is if the third term also had an x. When you're canceling, it has to be all or nothing. Either every single term has that factor that you cancel, and if one term doesn't, like this one, you cannot cancel anything. So this expression right here is actually simplified completely. So that's that. All right, so good. So we have another tool to use. We can use logarithms to separate out complicated arguments, or logarithm rules to separate out complicated arguments of logarithms. And it makes everything just a little bit easier. Okay, so let's look at the natural logarithm of some absolute values. And this is number 25 in your homework set. And we're going to be finding the derivative of the natural log of the absolute value of secant of x. Okay, so if you guys remember our strategy for absolute value when we're finding derivatives or we're taking limits, and remember a derivative is a limit, we separate it out into 2 rules, right? We have to figure out where the x makes the secant positive and where x makes the secant negative. And so I think trig is very visual, so let's go back to our unit circle. And secant is 1 over cosine, right? And cosine is the x coordinates on around the unit circle. So where are the x values positive and where are the x values negative? All right, in quadrants 1 and 4, cosine is positive, and then in quadrants 2 and 3, cosine is negative. Okay, so this y-axis marks where it changes, right? So these are going to be, let's see, that could be like pi over 2, and then 3 pi over 2 is where the sign of the cosine changes, okay? But we also know that it goes on forever. So once we go here, it could be pi over 2, 1 rotation plus pi over 2. So really we're looking at pi over 2 plus a rotation, right? And one rotation is 2 pi. And we can do that for however long we want. So k could just be, 3 rotations, 4 rotations, 5 rotations, stuff like that. And likewise down here, it's going to be switching from negative to positive at 3 pi over 2 plus any amount of rotations. Okay, so why are we doing this? We're doing this so we can figure out a rule. So now the natural log of the absolute value of the secant function can be separated into 2 rules. One rule, when the secant is positive. When the secant's positive, it's just going to be the natural log of the secant of x, okay? Because it's absolute value. Absolute value always has to be positive. And then over here, in the second and third quadrant, the cosine is going to be negative. So how do we make a negative number positive? By taking the opposite of it. So when it's negative, it has to be the negative secant. Just think, if it was -1, how do we make -1 positive? We look at the opposite, and then minus minus becomes plus. So same thing over here. Okay, so this is going to happen. The x is going to be positive from this point down here all the way up here, okay? And I'm going to have that be our starting point. So maybe instead of 3 pi over 2, I'm going to say negative pi over 2. So I'm going to start here, and I'm going to go all the way up to here. So negative pi over 2 plus 2 pi k to pi over 2 plus 2 pi k. Okay? And then when we hit this spot up here, we're going to switch to our other rule because cosine is going to be negative. So now x is going to be between pi over 2 plus 2 pi k, 2 pi k, less than x, less than 3 pi over 2, just kind of going around the circle, plus 2 pi k. All right, and remember, we exclude the zeros, which is at the pi over 2's, because 1 over 0, secant's not defined right there. Whew. Okay, guys, so why are we doing this? Well, we want to find the derivative, okay? And so, but we can't take the derivative of the absolute value, so we had to separate it into 2 rules. Now we're ready to take the derivative. So I'll switch colors so we know we're ready to take the derivative. So now the derivative, I'll just call this function f. Let's do the derivative of the natural log of the secant. So we'll do the top one first. All right, well, it's a chain rule. So derivative of the outside function is 1 over x. So 1 over the input. 1 over secant x. Chain rule tells us to multiply by the derivative of our inside function. What's the derivative of secant of x? Secant x, tangent x. Okay, good. And then the secants will cancel. Just ends up being tangent x. Lovely. All right, rinse, wash, and repeat for the bottom. All right, so again, derivative of natural logarithm is 1 over the argument. And then what's the derivative of the inside function? Well, that negative sign will make it negative secant x tangent x. And then look at that. The negative signs actually cancel out. And we're still left with tangent of x. We're still left with tangent of x. So because they're both equal to each other, we don't have different derivatives for those 2 separate rules. That means then that the natural log of the absolute value of the secant of x is equal to tangent of x. All right, and then actually, it just ended up equaling to natural log of just the regular secant of x, because when we had to take the opposite of the argument, the negative sign just ended up canceling. Okay, so it actually leads us to another little fun tidbit. If we're going to take the derivative of the natural log of the absolute value of x. It's just like taking the natural log of x. It's just 1 over x. We don't have to worry too much about, two different rules. We don't have to worry about two different rules like we just did in that example. So there you go. All right, so let's go ahead and pause here. We're not done with this section. When we come back, we're going to learn about logarithmic differentiation.